So I got an email, this may be already now several months ago, on a project where trusses had been put up on a pretty large project. It's not in Gauteng, it's actually on a coastal area in South Africa, where a number of angles that were used to construct the trusses, these pretty heavy, let's call them trusses, long span trusses, had laminations in them. Now, it's highly unusual for angles to have laminations in them. And I'll explain what laminations are in just a second here. But essentially some sort of defect in them. And they wanted to know what to do about it. So, of course, the first curious thing about it was that these trusses had already been erected. And so, of course, my first question to the engineer was, I mean, these are not problems that just occurred. They must have been there right from the beginning. So how did they get missed? And really, we couldn't find answers that were, let's call them, easy answers to these kinds of questions. And then, of course, this went back to the fabricator, back to the merchant, and ultimately back to the steel mill, which is where the laminations started. So now that's a very expensive mistake in general, because now you've put up a whole bunch of trusses that are essentially have defective angles in them, and in many cases that would result in having to essentially have to take down the whole truss and replace, which is a very, very expensive venture, not just from a point of view of material expense and erection and fabrication, but also just from a programming and scheduling point of view for the owner of the building. So so we were curious to find out how such a big issue could have occurred in South Africa, where we have a pretty good quality of steel production and fabrication and supply, along with some pretty good engineers who do these projects. So we wanted to find out what's going on. So that's essentially where this whole thing started in its most recent iteration. But laminations have been an issue also historically, especially when Highveld used to produce steel in certain types of, let's call it fabrication configurations and connections. So I also want to address that, which is a slightly older problem that might still persist today. So before I go into what laminations are, let me just say that the thing that we discovered was that there was a breakdown in the quality process of the whole supply chain. And that's sort of the big lesson here, is irrespective of the actual defect, the problem had been missed by the mill, obviously. Fortunately for the big mills that are in South Africa, it wasn't one of them. It was a smaller mini mill that had produced the angles. But then the defect had also been missed by the merchant, which was a large merchant. Then it had been missed by the fabricator, who's also a large fabricator, and of course by the erector as well. So there was a breakdown in the quality system, and that's the thing. That's the sort of, let's call it, the overall lesson that we learned from that problem. But let me get into the technicalities of what we studied and found out. These laminations are typically an outcome of the manufacturing process. So the way a lot of steel is produced is that it's rolled, and what that means is essentially you make a big chunk of steel, molten steel, and that has to somehow get transformed into the final product. There are many different ways of doing this. If you're using like ignits and stuff, which is small little chunks of steel that have been cooled and are yet to be reprocessed, which is an older method, then these laminations are quite common because there's a lot of impurities that get included into the new rolled product. And it's typically sulfur we're talking about here. But if you're using the continuous casting process, which is essentially what a lot of the larger steel mills use, which is molten steel goes and gets continuously cast into a plate that then gets rolled into a thinner and thinner and thinner plate, then this should be a less frequent problem, but it can still be a problem because the inclusions can still be there. And what happens is these sulfur crystals essentially start getting pushed into the center of the steel, and essentially that impurity now sits in a central layer of a steel plate or member. And at any opportunity, either because the steel is being loaded in that transverse direction, which is called the Z direction, or simply as it cools down, it starts separating. And that separation, that delamination of the steel along the length of the steel through the center of the steel is what we call lamellar tearing or laminations. So that's sort of the very simplistic explanation of how it arises. It's from the production process and the inclusion of impurities, typically sulfur, that gets pushed into the center of that steel as it cools down.
You've touched on some of the technical queries that we've had regarding laminations. Are there any other kinds of queries that come up, or anything else you want to highlight that you know our engineers need to be aware of?
Yes. Like I said, there are actually two different types of problems that arise here. One has to do with the actual material supply, and the other one has to do with fabrication. Now, let me just address them separately here. When it comes to material supply, and this is also what came out of our investigations of that question that came in, the industry is somewhat fragmented now. So what I mean by that is, for instance, a steel mill might have a whole lot of material scientists employed, but these guys are not necessarily very knowledgeable about, let's call it the supply chain, which is essentially what kind of quality control is imposed by merchants or fabricators, or what kinds of standards would govern the supply of materials. Or a merchant would have a person who's in charge of quality, for sure, as in this case, they should have had one. But the standard method here is, oh, you know, we're used to receiving products from good, credible steel suppliers anyway, so we don't have to do any involved type of, let's say, visual inspection. So this type of thing exists with the steel merchants. So even though they have a quality person, they're not necessarily doing the work to catch these problems. And then, of course, at the fabrication engineering level, there may be a complete lack of knowledge about how to actually identify these problems or what to do about them once you find them. This is what we discovered as we investigated this matter. Now, a good portion of the reason why people don't have in-house expertise, of course, is because they can't afford it. A lot of these contracts are pretty harsh these days. They don't look at the quality holistically. Everyone is trying to essentially minimize their own risk to be competitive. And what that means typically is that, in general, overall, the quality can get compromised, exactly as it happened here. Now, one item that came up, which is unfortunate, is, okay, if you don't have in-house expertise, where do you go? Now, this is an interesting question, meaning, where do you go for help? Now, we get to see the questions and the problems after they've occurred. So all these trusts had already been put up, which is really too bad, because at the Steel Institute, of course, we have a good amount of knowledge, or we know the people who have knowledge about these kinds of things and how one would have been able to deal with such issues. So why the industry did not come to us in the early phase of this project is also another interesting question. So clearly, it's not only a lack of in-house expertise in laminations, but there may also be a great deal of lack of in-house expertise in knowing where to go when you face a problem. So this is the second part that came up, which is obviously a problem. Now, just maybe switching gears here, the other problem that's emerging is that the supply of steel in the country is now significantly more diverse than it was before. What I mean by that is there are significantly more merchants bringing steel into the country. There are significantly more steel mills involved in producing steel and supplying to the South African market. I think I can count maybe 11 mini mills in South Africa right now. So this is leaving aside Mittal and Highveld. There are another 11 or 13 smaller steel manufacturers who are making everything from rebar to angles to channels. That's a huge amount of diversity that's been introduced into the market. And then, of course, that's only about half of the consumption of steel in the country. The other half is coming from abroad, which means there's a huge diversity in the amount of steel that's coming in general. And our industry, I don't think, is yet ready to deal with the kinds of quality issues that might come up as this diversity explodes. And this explosion has happened literally in about a decade, which is not very long from an industry point of view. So that's the second aspect that has emerged now, which is our industry is not yet ready to deal with this diversity of steel and how to deal with it. And that I'm talking about the engineers who specify the steel. I'm talking about the fabricators who use the steel, the merchants who buy it. All of these guys are not yet geared for the kinds of diversity that we have in the market. So that's the item that I wanted to highlight that came out of this query.
Right. So, Amanuel, in your opinion, what do steel producers need to do to avoid these kinds of issues that come up with laminations? What procedures and processes do they need to have in place, or do you think they need to focus on to avoid these kinds of issues?
Well, the steel mills, it's kind of hard for us to influence them. You know, they have to produce good quality steel. What that means is there has to be ductile. Now, there are different ways for them to achieve ductility in that steel. The most important one being trying to reduce inclusions using processes that don't result in laminations. I already mentioned, for instance, continuous casting is a type of process that typically eliminates this in the majority of types of steel. But it's also important for steel mills beyond the production quality, which is not exactly in our purview or control, to have people who educate the people who buy the steel. So for instance, I think it's very important for steel mills to start educating merchants on steel, especially thicker steel, which can exhibit lamellar tearing when you connect it in specific ways. And what I'm talking about here would be if you're making a box section, for instance, with an L shape, or if you're making a cruciform. These are the kinds of connections that have issues with lamellar tearing, because there's a lot of cooling of welds that happens that pulls that steel apart. So for instance, if you're designing a box section and the steel is over 20 or 25 millimeters thick, it's important for the steel mill to know what the application is, where it's going, and inform the merchant that the steel may or may not be appropriate for such construction. Or the merchant should have the expertise to be able to ask such questions. And this is now where everything is falling apart. Of course, it falls on the engineer ultimately to say, I'm designing a thick piece of steel. It's going to be used in a cruciform. And it's likely that this is going to be vulnerable to lamellar tearing. So I need to be careful with what kind of steel I'm going to order. Now, of course, we can get into the technicalities of what that is. Essentially, what do engineers have to do, what do fabricators have to do. But from the point of the steel mill, I would say that they have to start educating their clients. Because, of course, ultimately, when the problem does arise, they are also liable, as they were in this situation with the angle. Now, so I would say education is the key component, in addition to, of course, fixing their processes of how they produce to be able to get rid of these inclusions or switch their processes so that the steel is not vulnerable to lamellar tearing.
So, are there any questions from any of our participants?
I've got a question,
Okay.
Denise and Amanuel. Obviously the angles that were in use in Durban, the ones that failed, they must have come with a test certificate. Was there anything on the test certificates that might have indicated that they were substandard in any way, or was the problem related to the welding detail or the connection of the gussets? I presume it was a failure on the weld to the gusset.
Yeah, so that's a good question, Dave. Now it's interesting. So the merchant who bought the steel is a large merchant, and they did a good amount of due diligence in the sense of collecting documentation. And the most basic of those would be the mill certificate. So there wasn't an issue with the mill certificate as such. Of course, the mill certificate simply says to which standard they've produced the angles. Now, where we sit today is none of our standards, EN 10025 or the other ones, refer to lamination at all, because this is an old problem. So we've gotten rid of it. In a sense, it's not in any of our standards anymore. So, of course, that basically means that the steel mill essentially complied with our standards, even though the product was substandard, because the standards don't say anything about lamination. Now, the issue, interestingly, in this particular case, did not arise from a connection. Rather, it arose because the actual angles were full of laminations, even where there were no connections. So now that's a problem, because it goes back to a very old problem. So laminations and lamellar tearing in connections is still a current problem for thick plates, especially from some steel mills. But to have laminations in angles is really a problem that we should not have these days, as in, like, it's a very rare problem. So it was very unfortunate in that sense that it was that substandard, and that it didn't get caught, because the lamination wasn't just in one or two angles, it was in several angles. And that's essentially what I'm raising here, that there was a failure in the overall quality system.
Well, how would you have spotted the laminations in the first place? I mean, the lamination, as you say, is usually in the center of the section. And it's not really visible until you've loaded that or stressed that member. So how would anybody have ever spotted it in the first place?
Yes, so yeah, it's very hard to catch in a 12-meter or 6-meter long angle, unless it's visible at the edges, obviously. So I would say that the most likely place you can catch it would be during fabrication, as you start cutting these angles.
Yeah.
Yes. So now, of course, stopping it then would make a lot of sense as compared to going and erecting the stuff, because then the costs are somewhat contained, even though it's still too late, but it's somewhat contained. Now, I know some of these merchants also do some processing, what they call, what do they call it, value added or something, where they cut the steel for the fabricators. So it could also get caught at the merchant in some cases, like Max Steel or some of these large merchants do added value service.
But I mean, sure, my only experience of laminate tearing, it's not it's not the full length of the member that's affected. It's like a small section of it. Yes. So unless you start cutting the section, you're never going to spot it. Or
I can show you some pictures. Yes, let me share my screen here. I don't know if I can share screen. I have a picture of this one. Oh, host is disabled. Okay.
Okay, you should be able to share now.
Let's see. Oh, there we go. I just want to share a picture of this particular. So this is an actual picture from this particular question thing that came up. And as you can see, you're right. You're not going to see it everywhere, but in this particular case, it became visible during fabrication. Let's say, I would suspect, because of course that's why it's visible after it's erected. So,
but this looks like it's been done on some automated process. So there's actually no human being actually physically looking at that end section.
Right. Yes? Correct. Yes. Yes. So, and this is exactly my point now, is something has changed in our market. Let's say, I'm summarizing it as diversity of supply. I may be off on this, but this is my conclusion. The diversity of the supply of steel has expanded dramatically in the market. What that means is that the industry now has to gear up in some new way to catch these things before it's too late. So, and I'm not exactly sure what that is, but at a minimum, that means we may have to institute a pretty, let's call it serious level of visual inspection of the steel before the steel goes to site. I think that's reasonable. Meaning, yes.
Amanuel, sorry, I butted in. My apologies, but I'll finish anyway. Was this particular steel batch, the one in the failed trusses, was that sourced from a South African mill or a foreign mill?
A South African mill.
Okay, so that's quite significant. So
Yes.
it's not as if to say, well, it came from China and it's all, everything that comes from China is suspect. So it was a local mill.
Yes, yes,
Okay.
and I'm including that when I say diversity of supply now, because, like I said, there are 13 mini mills in this country now, which is relatively new in the sense of um, meaning the market here is used to having these big mills, a few of them that supply a lot of the steel in the market. That's how the industry is set up. Now the Highfeld is relatively gone. I know they do a little bit of rolling, but they don't produce much anymore. Now, what's interesting is Highfeld's plates used to have this issue a long time ago. For connection, they used to be vulnerable to some types of connections. So it's not completely a new problem, but that problem was known, and somehow people knew how to deal with it, and engineers were aware of those risks and would be careful when specifying those connections. What has happened since then is that obviously Highfeld is gone for the most part, and there are whole new entrants in the market. And in addition to those, there's a whole bunch of imports that are coming in from outside. And of course, a lot of pressure on prices. So all of this has conspired to bring about these kinds of problems. And this project was just the most egregious, but there have also been other projects where this has come up. That's why, of course, we made it a topic of discussion. So it's not the first one. So Dave, you're correct in that it is a new problem, and it's a serious problem that requires some action from designers and fabricators.
Would it be prudent for the Steel Institute to issue, as they have done in the past, a technical paper broadly issued to the industry to say this is now a significant issue, and we propose, at very least on the projects, that a new regime of checking be instituted in such a way as to be able to try and catch it without any rigorous testing being carried out?
Yes, so we did do a communique of some sort. Like didn't we do some sort of PR thing? Didn't we?
We did. We've got there is a technical article that I can send through
Okay.
to you that we did do, David, and then that does just detail. But I think perhaps expanding on that and adding in just some of the concerns that are raised within this forum, just augmenting that paper that has been already created. Amanuel, just a question from Reed. Does weld lamination occur frequently amongst automated welding or worker welding?
No. So the main issue where lamellar tearing becomes a risk factor is typically one is the thickness of the steel, meaning the steel that's being attached, and two is the configuration of the connection. So that's why I raised. So if you have a plate, and let's say you're making a cruciform shape, or if you're attaching a flange onto a beam, a flange of a beam into the flange of a column, or if you're making a tube section using a built-up box section where you're attaching one plate into another plate. Essentially, any time that you're pulling on through the thickness of the plate, then you have some risk of lamellar tearing. And of course, why weldments would create that is because the weldments themselves are quite hot when they're getting welded. And as they cool down, they start pulling the steel apart along its length, meaning try to tear it apart. And that's typically the types of connections where you'd see lamellar tearing being a major risk factor. So, and there are many, let's call it methods of reducing this, all the way from how you actually plan your welding, how much preheat you put into your steel, how fast you let it cool down, the thickness of steel that you order, what type of steel you order. So for instance, Dave just raised an interesting question of, well, people have to now do more stuff. Now, what is more? So the worst thing, the worst outcome of this would be all the engineers went out there and said, look, we don't trust South African steel supply. What we want to do now is we want to go and order everything to EN 1164, which is essentially a lamellar tearing standard in the Euro norms, that essentially says that the steel mill has to do several checks to make sure that it qualifies for a certain type of use. And it comes in different criteria, obviously. Now, if engineers did that, it's immediately, that will raise the price of steel immediately, because there's a lot of work that the steel mill has to do now, essentially ultrasonic testing and various types of other tests, before the steel is even shipped off to the merchant. That's not what we're looking for, because we assume that a lot of the steel production methods now are good for most of the work that we do. If you're doing something specialized on a bridge and you're doing a connection that is very vulnerable to lamellar tearing, yes, it does make sense to specify the steel to EN 10164. But if you don't do it and you do it the normal way, and then you have lamellar tearing, what do you do? And then there's obviously the whole also, let's call it regime of standards and expertise on acceptance criteria. What that means is, well, what do you do with this thing that now has this defect, just like the truss we discussed? It doesn't mean all the truss have to be torn down, but now you have to do a lot of work to try to figure out what to do about it. And that's a whole, what we call acceptance criteria, which is its own, let's call it, area of work. So I don't know if that answers it, but that's where we sit.
In my early career, I did a lot of work for the atomic energy in the UK, and lamellar tearing became a problem for them on moment end connections, particularly you're using a thicker 25 mil and upward end plate. And they eventually barred the use of anything thicker than, say, using a very thin plate with stiffness was a way to get around this issue.
Yes.
That's my only other experience of lamellar tearing that I've ever had.
Yes. So if you look at South African supply, I would say if you are doing, let's say, a box section with anything over 20 millimeters thickness, it will be an issue. Meaning it's something to think about. Or if you're doing a cruciform with over 25 millimeter thickness, it's something that will come up. It doesn't mean it will happen. I just mean it's something to think about from a design point of view, and to be careful about how the steel is supplied. But of course, the fabrication itself has a lot to do with this, as in, what is the process? What's the welding process like? It's not necessarily related to the welder quality, but rather the process that's used. Because I'm assuming, for instance, if you're doing a plate girder, those are all complete joint penetration welds. So whether it's robotic or it's done by hand, the process by which the welding is done is much more important than whether it's manual or robotic, as far as lamellar tearing is concerned. The slower it cools down, obviously it would help, because the demand on ductility on that steel is lower. But there will always be a demand on that steel, meaning if that steel is not ductile, if there is some imperfection in that center layer of that steel, it will go through lamellar tearing. And then the question becomes, well, is it acceptable or is it not? Maybe if you want me to show it like graphically here, I may have let's see, maybe I may share my screen again. There was this presentation that I did before. Let me just share my screen. Oh, sorry, Denise, am I able to share? Yeah, there we go. Let me just go here. Okay. Oh, okay. Let me share my screen. Go here. So just to show you what I'm talking about here, these are the types of connections that we're discussing here. So these would be, and maybe I should put a whole course together on this, because this is actually a very involved topic in general. So because it addresses both the supply of steel and how do you specify the supply of steel. There are all these topics of S's and E's and Z's that you have to learn essentially on ductility of the steel. They're all essentially different descriptions of the ductility of steel. And then there's a lot of stuff to think about in terms of how you specify the actual connection, which is for the engineer. And then there's a whole bunch of stuff on how you actually do the weld and how you implement the weld, which is for the fabricator. So this topic is in fact quite comprehensive in the sense that it involves everyone, the whole industry. But the types of failures we're talking about are essentially where you have a plate and typically it should be a thick plate, but as we saw with the angles now, even the thinner materials could be vulnerable to this kind of tearing. With a plate welded perpendicular to it, let's say, essentially even fillet welds, and as those welds start cooling, essentially they're pulling this plate essentially to separate, and that's what's going on here. Again, you see that with this kind of box attachment, what they call the L connection. This is by far the most vulnerable type of connection to lamellar tearing because it's at an edge of a plate. So this condition here with an L shape is by far the most vulnerable to this type of stuff. So this is if you have a connection of this type, you would order something that is more ductile than if you have, let's say, a cruciform shape, which is the one on the left here. But you can also have it in this kind of configuration on the right, which is unusual for most structural engineering applications, where it's the plate on the right that's actually tearing from the type of from the fillet weld essentially cooling down and pulling it apart. But these two on the left would be the more typical cases, what are called the L shape and the cruciform. And the L shape is significantly more vulnerable than the cruciform. And then of course, once you do have it, there's a whole yet other area of study to say, well, what is acceptable? And that in itself is also very much an engineering exercise, because you have to find out, well, to what level is the thing stressed? Is that tear acceptable? How much tearing is there? How much tearing is acceptable? And there's an EN standard 101.60, which addresses this topic in general, in a much larger sense of, it's a lot of ultrasonic testing and a lot of engineering, essentially. Again, very much involving the engineer and the fabricator, or the erector, if the thing has already been erected, unfortunately. So this is a very involved area. Maybe we should do more research and put a whole course together for it if this becomes a more common problem. Let's hope it doesn't. But it's quite involved.
So, Amanuel, what are some of the preventative steps that merchants and fabricators can take to guard against supplying or fabricating sections or any sort of steel that is prone to lamellar tearing?
Well, the first thing is to acknowledge that the steel now comes from so many different places, and that the merchants themselves are under so much pressure to be competitive, that they're buying from a whole bunch of places that they've never bought from before. I think this is a very key thing for everyone to accept now, right? The pressure is high from the clients in terms of the pricing. Now, the fact that the clients, in a way, might be shooting themselves in the foot by putting sometimes unreasonable pressure on the steel suppliers, we have to just accept, meaning that's just how it is now. A lot of developers, for instance, if it's for a building or for some other types of project, might be controlled by QSs who are very diligent on their financial aspect of the project, but may not be very knowledgeable from a technical point of view. So that pressure is on. Then the merchant now has to understand that they carry a huge risk, which is now they have to sell steel at a cheap price, but they still have to be able to secure steel that is fit for purpose. So not all the steel that they supply needs to be highly ductile, but a good portion of it needs to be highly ductile, especially those pieces of steel that are going to go into structures that are critical and components of structures that are critical. And now this requires a great deal of in-house expertise at the merchant, meaning essentially almost the merchant has to have someone who understands engineering and fabrication, which is very unusual these days now. So, or uncommon, let's say. So I would say from the point of view of the merchants, there's some need for investment, either in in-house technical competence or somehow outsource that activity to someone else who can help them with it. So that's what I would say about merchants, is they're essentially, there's a huge scarcity of technical talent in the merchant community now. This is just what I've observed. So that would be the merchants. When it comes to fabricators, not a lot of fabricators don't have in-house engineers anyway. So they have to rely on the consultant. Now, that doesn't mean there's nothing they can do about this. So they get a piece of steel, which has already been specified by an engineer. But I think they are a very key component of the quality control system of the whole process, because they're the ones who start cutting the steel and putting it together. And they're the ones that should be able to see if there's an issue. That's it. That's the time when it is most economical to catch and stop the process. Now, once it's past that stage and the thing has been fabricated, or it's been shipped to site, or even worse, erected, by then, I would say, essentially the whole thing is failed in the sense of from a project point of view. So it's too bad that that's how it is, but it looks like the fabricators are going to be carrying the heaviest of the burden on this. And of course, they're going to try to claim from the merchants and the mills, but the way I understand it, typically the way it works is the material gets replaced, but the fabricator is not going to get much compensation from a point of view of time spent and fabrication and all that kind of stuff. So, so the risk is heavy and high on fabricators. That's why it makes sense for the fabricators to try their best to catch the problem early. From a point of view of, I think did you add engineers in there? What engineers?
I was about to ask about engineers. How can engineers protect themselves and their projects in the event that there is some sort of an issue with lamination?
Yeah, for the engineers, that's why I guess I was saying maybe we should put some sort of course together. There's a dearth of knowledge out there on this issue. There's already a dearth of knowledge in terms of just connection design in general in the engineering community. And then this is a specialized area yet of material supply somehow related to connections. So on at least from our side, from the institute side, there's a great deal of need maybe for education. But from the engineer side, I think there needs to be an awareness that now there is a wider variety of input of steel. The positive news for the engineer is that now they can actually build more economical structures because they can supply steel from anywhere, presumably. But there is a risk associated with quality, just because now the supply chain is not as tight as it used to be in the market. So it could very well be that the engineer, when they make a decision to go buy steel from some small mini mill, have to actually go and visit the mill at a minimum and ask what quality control measures are in place, actually ask to see products. Now, I used to do this when I used to do consulting in the US, and when we first started buying steel from China. This is now already 15 years ago. So we used to have to go to China to the steel mills there to see what kind of steel they produce. It's just the new. It's new. It's something new. It's a new supplier, and you do. It's not enough just for the engineer to go out there. You have to take a whole bunch of people who know about steel with you. Because the engineer is very unlikely to be able to catch such issues because we're not trained in that way, as in to be able to know what is missing in a steel mill and what is not from a quality control point of view. It may also be important if you're working with new merchants as an engineer to actually also do the same thing and go visit them. Because now, of course, in this particular case in South Africa, we have large merchants from whom we buy most of the steel, and you already have a good relationship with them. So the failure is at the merchant level. So I don't know what the engineer could possibly do, but maybe it makes sense for the engineers now to go to the merchants, even here, to go to Max Steel, to go to all the Trident, all the other guys who are still around, and ask what they're doing in terms of quality. This is just, even though these are companies you're used to working with, you may have to go back to them in a new way, essentially. So it's just a different environment. It's a new industrial reality, and the engineers have to adapt and start covering themselves for this kind of risk. Now, typically, the engineer doesn't carry a lot of risk in terms of bad quality of steel, but there is a minimum level of due diligence that's required from the engineer to make sure that the other parties in the construction are not exposed to risk. And one of them is to make sure that the supply of the steel is somewhat legitimate.
Emmanuel,
Any questions? David, you want to go ahead?
I've got a question here. We had a recent case of a plate that failed. It was a brittle fracture. The plate was called upon to deform, and as a result of a very highly stressed connection, and the plate failed. What we established was that the plate had obviously slipped in through the cracks in the quality control process. But our client at that time took a view that they said, because of brittle fracture, we want to specify more ductile plates for our projects in general, over the whole range, including rolled sections. And we had a job to convince them otherwise, and they wanted to use a normalized, in other words, normalized steel grade 350 WC plus additional normalizing, which would have added huge amounts of cost and delays onto their projects. In simple terms, would any of that, if we had to specify a much higher grade and obviously more expensive steel, would that make any difference to the problem of lamellar tearing?
That's a very interesting question, Dave. That has come up before, and that's what I said would be the worst case outcome. Would be if engineers went out there and started specifying steel that is not necessary or not fit for purpose in that sense, too expensive for its need. So in South Africa's context, let's say if you started specifying S355 J0 for every structure that you put together and for every rolled shape, I would say that's a huge amount of cost that's unnecessary, simply because it is not justified in our experience. And it may not necessarily solve the problem in any case. So for instance, you go and specify J0, all right? But the connection is specified in such a way that it makes the steel vulnerable to lamellar tearing. So the problem goes beyond the specification of the steel itself to how is the connection specified, to what level of stress is it loaded in its operation, what kind of fabricator is hired to do the work, who's specified the preheat and all the welding procedures. Because the problem is so much bigger, it would make much more sense for us to try to understand the actual issues and dive in and hit the problem where it exists, as opposed to a blanket solution of trying to find what your client was trying to do, which is to try to find a blanket solution. Because I don't believe it exists. It would make more sense to try to identify when are we having issues, where are we having issues, who are the problematic suppliers, and try to identify those and get rid of them somehow, either through technical expertise, through media, and through just being diligent about it, than to raise the price of all our projects by 20% on material. And in any case, still not solve the problem. That would be my view. I don't know how you dealt with it.
Well, we were able to easily show to the client, well, reasonably easy, that it was not necessary to respecify the steel because the majority of the projects did not fall in that category.
Right.
And of course, you had to fall back on the whole concept of the detail itself was deforming significantly, and it was, if you excuse the pun, pulling the ductility envelope to its extreme.
Right.
So we were able to convince him not to do that.
Yes.
And we were able to give a rational answer.
Yes. Ultimately the problem ends up being that if a detail is wrong, it doesn't matter how ductile a steel you order, it will crack. You know, like this is the issue of the we always discuss these weld connections that somehow have what we call a triaxial state of stress on them, essentially meaning that they're stressed in all three axes of the material. Any steel material that is loaded in a triaxial state of stress has zero ductility. That's just the mechanics of the problem. So that's why it is a much wider problem of the engineering, detailing, fabrication, welding specification, in addition to material supply. And so I think what you did is exactly what I've done, John, is try to convince them not to go that way. And one engineer from a large consulting firm here, when this problem came up, asked if they should specify, all steel to be supplied to 10164, EN 10164. And my answer was, no, don't do that, because it's not necessary yet. I mean, one day it might be necessary, we'll see, but not at this point.
This particular steel supplier, South African steel supplier, obviously has got to look at their own processes significantly.
Yes.
And how, and again, I don't know what the documentation is, or whether or not you have had sight of the documentation and the correspondence. How are they going to deal with their own quality processes in the future to make sure their product makes it and is safe for fit for purpose?
Yes, so what we did, at least from the institute point of view, is because they're not really our member or anything. Of course, they know about the problem very well because they had to replace all the steel. But what we did is we went to the merchant who is our member, and we said, how are you going to force them to change their quality? And that's the best way to approach the problem, because it's the merchant is their client, the steel mill's client. And they're much more likely to listen to someone who pays them, as opposed to some institute out there that has nothing to do with them. So we had a lot of discussions with the merchant. We gave a lot of technical support on what to ask for. And essentially what it comes down to is what Denise was asking before: what should the merchant do? The merchant now has to put together a program of some type that is imposed on the steel mill that supplies the steel. This is what should have happened in the first place anyway. Meaning the merchant should have some method of making sure that Newcastle ArcelorMittal can produce good steel. Meaning this is just how it should be. Now what the merchant typically doesn't do it because they trust what comes out of Newcastle. Okay, we understand, because they've been buying from them for the past 50 years or 70 years or however long. But now we're saying there's a diversity of supply, there's many more players, and the merchants now have to, let's call it again, tighten the system and become more responsible for this, because they are carrying the risk. I mean, they essentially they supplied, bad quality steel, and these are big merchants.
I recently had a problem whereby I'd specified an angle as a stiffener 355. The angle failed. They actually pulled right through the member, and when it was tested, that piece of steel was actually less than commercial grade. How can you possibly catch or stop something like that? Where the fabricator, in an attempt to reduce his cost, has just bought steel from anybody.
Yeah, this is exactly it. This is what I'm calling the diversity of steel supply. This is a big change. It's not a small change, and the implication is quite big. And somehow we all have to wake up to it, and maybe we need to do more in terms of, from a PR point of view, from the Steel Institute. But we are focusing on essentially trying to get the merchants to do the bulk of the work. We think that's the right intervention from our point of view.
Now I have an Antiques Roadshow question for you.
Yeah.
we watch the Antiques Roadshow, and of course what they do is you get the expert who holds this vase, a beautiful ceramic vase, and he says the way you test if it's got a crack is you just flick it with your finger and it goes, the other goes ding ding or tuck tuck. And so is there some kind or any kind of simple test like that we as engineers, fabricators, erectors, and so forth, even manufacturers, can carry out on the steel? Or has there been one developed, or is there one, people looking at something like that?
Yeah, so the standard approach, leaving aside the steel mill, which have their own methods of doing these, let's leave them out of this for now. But EN 10164, for instance, would require that the steel mill actually do quite a bit of ultrasonic testing, which is one way to catch the problem. It's not cheap. It is an NDT method that costs some money and expertise. If you were to do it yourself, so what you're saying is once the steel is arrived at this fabrication shop, I would say at a minimum, and that's my preferred method, would be visual inspection of all the steel that has already been cut. Because of course, if it's not cut, then you can't see it. This is what Les was saying earlier. That would be only for the first. I'm not saying necessarily that every single piece of steel that has ever been cut in a fabrication shop should have been visually inspected. But to train the people who work on that steel to just look at it and report anything that they see as just a standard practice for all the boiler makers would be a huge leap in terms of quality, because a boiler maker is just going to pick it up. They're going to move it somewhere. They're going to put it in a bundle and lift it on a crane, and they can see the end. I mean, it takes maybe 10 seconds to just look at it. But this requires a great deal of effort from the fabricator now, because they have to essentially tell their workers, look, try to see if there are problems with the steel. Now you would expect this to be normal for anyone who's handling steel, to try to make sure that the steel looks about right. But we know that this is not the case, just from that one example with the trusses, right? So I would say visual inspection, Dave, but of course, ultrasonic would be what would be specified. Let's say if you were doing EN 10160 acceptance criteria, they would tell you do ultrasonic and find out the probabilities, find out how many of them you have, and they will give you a probabilistic method of how to approach this.
From the picture, the one picture you showed there, you could see very clearly on the saw cut end of a beam, or the angle rather, where the cracks were, and that was great. What about a guillotined end, a guillotine cut end? How does that behave, or can you see it as clearly?
So now we're addressing the issues of lamellar tearing in steel that has already, let's call it, where the defect is already visible from the steel mill, meaning where the production was the issue. In that case, the method of cutting shouldn't necessarily be able to conceal it if you can find it exactly where that lamellar tearing has occurred. The typical problem would be if the lamellar tearing occurs during fabrication. Now that's an interesting one, because you may never be able to see it. Of course, those are the more typical problems with the thicker materials. And again, there's a caveat here, which is lamellar tearing is not common in rolled shapes. This is why this problem was so unusual, because that problem was long solved a long time ago. As in, even with the high-felt steel, we had the lamellar tearing issues only on the plates, not on the rolled shapes. So again, the fact that this has come back is really too bad, and that's why we're saying we have to identify the issues, separate them into their little categories, and try to hit them wherever we face them, as opposed to trying to come up with blanket solutions.
Right. Gents, we've got about 5 minutes or so left before we wrap up. If you'd like us to send you through some of the articles that we have written on the topic, just pop me an email. It's denise@saisc.co.za. That's DENISE. And then I will make sure that you get a copy of that article that has already been written. We are going to be having these technical sessions every 2 weeks. You'll note on the Steel Institute website, under the training section where these sessions are advertised, that there's a list of topics that we are planning on covering. But if there are any questions that you have in the meantime, or any specific topics or queries that you'd like us to cover in future sessions, there's always a little bit of an opportunity at the end of the session to bring up any other questions that perhaps are not related to the topic that we're discussing today. But if there's anything that you'd like to raise, you can do so. So any closing comments or questions? Les, is there anything that you'd like to remark on?
No, I think it's covered most things.
Grant, any questions or comments from your side?
Yeah, I think just thank you, guys. It's very informative. Looking forward to the future ones to come.
Yeah, nice to see you, Grant.
Great. Reid, any questions from your side?
I think Reid already thanked us and took off. You're muted, Denise.
Right. So I think we're going to close up if there aren't any more questions or comments. Thank you all for joining us, and do keep an eye out on the topics that are coming up. We do also have a couple of technical training courses that are coming up as well, that are CPD accredited. At the moment, these sessions we're just doing for information's sake, but we will have a look at potential CPD accreditation for the sessions. So that is on our radar. It was something that I think Reed asked about, or I can't remember who asked, but we are going to be looking at CPD. Oh, David, yes, thanks for that. Okay, so we look forward to seeing you again, and if you have any colleagues that are also members of the Steel Institute, do just let them know that these sessions are happening on a bi-weekly basis, and we would love to engage with you further.